Hello, my name is Guy Davies from DAS Environmental Expert, and I'm going to talk today about reducing NOx emissions from waste gas treatment systems. So I think the motivation is clear. NOx is a toxic gas. It has a big impact on the health. It's a precursor for ozone formation in the atmosphere. It can form acid rain, and it also has a small global warming potential. So what we see, these are really driving local governments to implement stricter and stricter emissions regarding NOx, and customers are beginning to do more and more to focus their activities on reducing NOx. So where does NOx come from? I think there are two main routes for NOx formation. The first is thermal NOx. That's typically formed at very high temperatures in plasma systems or oxygen-based burn wet systems, and really, the temperature is what drives thermal NOx. So we often see this in processes where we have CF4. We need a very, very high temperature to break those carbon-fluorine bonds. On the other side, the other route to NOx formation is fuel NOx, and this is produced when we have nitrogen in process waste gases. So what we see is CVD processes with N2O or ammonia. We see very high NOx emissions during the processing of those gases. So that fuel gas is quite hard to suppress in the system. So what are the different possible strategies to eliminating NOx? I think the first one that everybody talks about is primary reduction measures. This is really focusing on the actual combustion and optimizing the combustion process within the abatement system. Unfortunately, this is relatively limited effect in comparison to secondary measures. These are typically highly efficient, but they do come with the downside of a secondary abatement system that drives cost, it drives extra media, and of course the footprint in the subfab is always at a premium. Here we have a typical burn wet system. And you can see on the left-hand side a lot of the typical gases that we have to treat. Here we can see we have both CVD and etch type gases. And coming out of the abatement system, there are two emission streams. The first stream is the waste gas components, and there we typically see carbon dioxide and NOx, and also fine dust from the oxidization of silicon or tungsten-containing compounds. In the water, we also see those oxides that are caught by the scrubber, as well as numerous other byproducts. If we go and look at some primary NOx reduction measurements, one technique is fuel dilution. And here I can minimize or reduce the amount of NOx emissions by diluting the fuel gas. This has the effect of reducing the combustion temperature in the reactor, and so minimizing my thermal NOx emissions. Okay, this also has the downside that I move away from my optimum temperatures for effective DRE treatment. So in principle, the concept of primary emissions, or let's say fuel gas dilution, is very simple, but in practice it's much more complicated. I have multiple inlets for my process tool. The process is always at a different time point, and so I'm mixing lots and lots of gases at the same time. I've got a time delay of those gases reaching the abatement. So it's difficult to turn these sort of primary measures into a really effective NOx reduction program. So if we think about, okay, primary NOx emissions are not going to get me to where I need to be. So if I think about secondary NOx measures, there are typically four processes that are well known within the industry. The first one is wet chemical oxidization. This process is very slow, and so we need a very large wet scrubber to reach effective oxidization of the NOx. Another technique is to use a dry oxidization method with ozone. Unfortunately, this requires a pretty high energy consumption to produce the ozone, followed up by, of course, a wet scrubber. The technique that we at DAS have implemented is a selective catalytic reduction system. So here, it's a very effective way of treating NOx, but we also need to heat up the waste gas. and we need to dose the catalyst with ammonia or urea. A last possible method is using a non-catalytic reduction method, but unfortunately this needs even higher temperatures than the SCR method and is really not as efficient in treating the NOx. So from our point of view, the SCR method was the route we chose into developing a product. So here's a schematic diagram of how the system could look like. On the left we have our bay of abatement systems, and then I'll just highlight the main sort of process steps in the NOx treatment system. So the first thing I need is a dust filter. This is pretty essential as I really need to protect my catalyst from dust contamination. Second step is a heat exchanger. I'm really looking to optimize my energy efficiency of the system, so recovering the waste heat out of the exhaust is a key step in saving energy. I need a gas heater to meet the sort of activation temperature of the catalyst of around 200 degrees, the ammonia dosing system, and then obviously the waste gas flows out through the heat exchanger. So how does this system perform in practice? Here we have 12 hours of live data from the system. You can see we have peaks of up to 1000 ppm of NOx. Average over this 12 hours was 170 ppm on the inlet, and after treatment we had 5 ppm on the exhaust output. So great results there. If we look at long-term performance over a month here, the average NOx DRE performance we achieved on average 97%, which was above the target specification of 95%. So we at DAS developed the product TSUGA as a standalone solution for treatment of NOx, and it also comes with the secondary effect of eliminating all particles from our waste gas flow. So as I said, the design requirements were treatment of NOx of up to 95% efficiency. Obviously ammonia is also not a very nice chemical, so we really minimize the slip by control of the reducing agent down to about 10 ppm, and we really optimize the energy demand by the use of the heat exchanger in the system. A sort of secondary effect of the system is that we also eliminate all the dust, so we have very good PM 2.5 performance with the implementation of the membrane on the inlets of the system. So in summary, we showed that NOx is really a byproduct of plasma or burn wet abatement systems. Etch processes tend to drive thermal NOx, while CVD processes drive fuel-based NOx. We showed that thermal NOx can be reduced to some effect by optimizing the combustion process, but we really don't reach the sort of values that I think we're expecting or we really require moving forward into the future. So the product TSUGA, using SCR technology, can really eliminate NOx from processes where we have high NOx emissions, with also the secondary effect of virtually eliminating all particle emissions as well. Thank you very much.